we're going to derive the formula for the moment of inertia of the solid cylinder. So here we have the cylinder, this is the radius r, the length l. We know that the moment of inertia is the mass times r squared. R is the distance from the edge of, or the axis of rotation to the mass. So if we put a cylinder here, this is like a shell, cylindric shell that has radius x and wide dx. The moment of inertia of this shell, would be the mass times, well, actually it would be the moment of inertia, because this is a very small moment of inertia. Would be the r squared. R is the the distance at which the particles are from the axis of rotation. So this is the axis of rotation, and each mass or each particle is at the distance of x from this axis of rotation. So we have that the I would be the m times x squared. Now we know that density is equal to mass times mass per volume, and mass would be equal to density times volume. The volume of this shell, cylindric shell, is, if we unfold this, we would have something like this. This is the length, this is the circumference, that is 2 pi x, and this is the width, dx. So the volume would be 2 pi x l dx. So the mass would be the density times 2 pi x l dx. Now we will take infinitely shells, cylindric shells, that have radius from x equals 0 to x equals r. So we are summating all the moment of inertia of these cylindric shells. These shells are like empty shells, so it is not a cylinder, a solid cylinder. But we are taking the moment of inertia, let's say, of this shell. Well, the first shell would be radius x equals 0, so it would be like to stay line. Then this shell, and then a bigger shell, and then a bigger shell. So it is like the bigger shell has inside the other shells. So at the end, in summing all the moment of inertia of these cylindric shells, at the end we will have the moment of inertia of this solid cylinder. So we have that the moment of inertia would be the integration from x equals 0 to x equals r of the mass, that is 2 pi density x l dx, times the radius squared, that is x squared. So we have the moment of inertia is the integration from 0 to r of the I, and the I, we saw that it was the mx squared. So here we have this times x squared. So we have the let me take out the constant, so it will be 2 pi l rho times the integration from 0 to r of cubed x dx. So the moment of inertia would be 2 pi l rho x to the 4th power over 4 evaluated from 0 to r So when x is 0, all this would be 0, so we use care when x is equal to r, so it would be 1/2 of pi L rho x r to the fourth power. And now just let me substitute again the density. We know that the density is mass per volume, and we know that the volume of the solid cylinder is the area of the base times the length, so it would be pi r squared times L. So we have that the density would be mass over pi r squared L. So here we have that the moment of inertia is 1/2 of pi L times the mass over pi r squared L times r to the fourth power. So the p cancel, the L cancel, this r squared with this r to the fourth power is square r, and so we have that the moment of inertia of a solid cylinder is 1/2 of the mass times the radius squared. And we will use this formula in the next video to derive the formula for the moment of inertia of a solid sphere.